The Semantic Web is an extension of the web through standards by the World Wide Web Consortium. The standards promote common data formats and exchange protocols on the web, most fundamentally the Resource Description Framework. According to the W3C, the Semantic Web provides a common framework that allows data to be shared and reused across application, enterprise, and community boundaries. The term was coined by Tim Berners-Lee for a web of data that can be processed by machines. While its critics have questioned its feasibility, proponents argue that applications in industry, biology and human sciences research have already proven the validity of the original concept. The 2001 Scientific American article by Berners-Lee, Hendler, and Lassalle described an expected evolution of the existing web to a semantic web. In 2006, Berners-Lee and colleagues stated that this simple idea remains largely unrealized. In 2013, more than 4 million web domains contained semantic web markup. Example. In the following example, the text "Paul Schuster was born in Dresden" on a website will be annotated, connecting a person with its place of birth. The following HTML fragment shows how a small graph is being described, in RDFA syntax using schema.org vocabulary and a Wikidata ID. Less than div vocab equals http://schema.org/ type of equals person greater than less than span property equals name greater than Paul Schuster less than span greater than was born in less than span property equals birthplace type of equals place. href equals http://www.wikidata.org/entity/q1731 greater than less than span property equals name greater than Dresden less than span greater than less than span greater than less than div greater than. The example defines the following 5 triples. Each triple represents one edge in the resulting graph. The first element of the triple is the name of the node where the edge starts, the second element the type of the edge, and the last and third element either the name of the node where the edge ends or a literal value. http://www.w3.org/1999/02/22-rdf-syntax-ns type http://schema.org/person http://schema.org/name Paul Schuster http://schema.org/birthplace http://www.wikidata.org/entity/q1731 http://www.wikidata.org/entity/q1731 http://schema.org/item type http://schema.org/place http://www.wikidata.org/entity/q1731 http://schema.org/name Dresden. The triples result in the graph shown in the given figure. One of the advantages of using URIs is that they can be dereferenced using the HTTP protocol, according to the so-called linked open data principles. Such a dereferenced URI should result in a document that offers further data about the given URI. In this example, all URIs, both for edges and nodes, can be dereferenced and will result in further RDF graphs, describing the URI, e.g., that Dresden is a city in Germany, or that a person, in the sense of that URI, can be fictional. The second graph shows the previous example, but now enriched with a few of the triples from the documents that result from dereferencing http://schema.org/person and http://www.wikidata.org/entity/q1731. Additionally to the edges given in the involved documents explicitly, edges can be automatically inferred. The triple underscore http://www.w3.org/1999/02/22-rdf-syntax-ns #type http://schema.org/person from the original RDFA fragment and the triple http://schema.org/person http://www.w3.org/2002/07/owl #equivalent class http://xmlns.com/fof/o.1/person from the document as http://schema.org/person allow to infer the following triple, given OWL semantics. Underscore http://www.w3.org/1999/02/22-rdf-syntax-ns #type http://xmlns.com/fof/o.1/person Background. The concept of the semantic network model was formed in the early 1960s by the cognitive scientist Alan M. Collins, linguist M. Ross Quillian and psychologist Elizabeth F. Loftus as a form to represent semantically structured knowledge. When applied in the context of the modern Internet, it extends the network of hyperlinked human-readable web pages by inserting machine-readable metadata about pages and how they are related to each other. This enables automated agents to access the web more intelligently and perform more tasks on behalf of users. The term, semantic web, was coined by Tim Berners-Lee, the inventor of the World Wide Web and director of the World Wide Web Consortium, which oversees the development of proposed semantic web standards. He defines the semantic web as a web of data that can be processed directly and indirectly by machines. Many of the technologies proposed by the W3C already existed before they were positioned under the W3C umbrella. These are used in various contexts, particularly those dealing with information that encompasses a limited and defined domain, and where sharing data is a common necessity, such as scientific research or data exchange among businesses. In addition, other technologies with similar goals have emerged, such as microformats. Tim Berners-Lee originally expressed the vision of the semantic web as follows: I have a dream for the web, in which computers become capable of analyzing all the data on the web, the content, links, and transactions between people and computers. A semantic web, which makes this possible, has yet to emerge, but when it does, the day-to-day mechanisms of trade, bureaucracy and our daily lives will be handled by machines talking to machines. The intelligent agents people have touted for ages will finally materialize. The semantic web is regarded as an integrator across different content, information applications and systems. It has applications in publishing, blogging, and many other areas. Limitations of HTML. Many files on a typical computer can also be loosely divided into human-readable documents and machine-readable data. Documents like mail messages, reports, and brochures are read by humans. Data, like calendars, address books, playlists, and spreadsheets are presented using an application program that lets them be viewed, searched and combined. Currently, the World Wide Web is based mainly on documents written in hypertext markup language, a markup convention that is used for coding a body of text interspersed with multimedia objects such as images and interactive forms. Metadata tags provide a method by which computers can categorize the content of web pages. For example, less than metaname equals keywords, content equals computing, computer studies. Computer, greater than less than metaname equals description, content equals cheap widgets for sale, greater than less than metaname equals author, content equals John Doe, greater than with HTML and a tool to render it. One can create and present a page that lists items for sale. The HTML of this catalog page can make simple, document-level assertions such as, this document's title is Widget Superstore. But there is no capability within the HTML itself to assert unambiguously that, for example, item number X586172 is an Acme Gizmo with a retail price of €199, or that it is a consumer product. Rather, HTML can only say that the span of text X586172 is something that should be positioned near Acme Gizmo and €199, etc. There is no way to say this is a catalog, or even to establish that Acme Gizmo is a kind of title or that €199 is a price. There is also no way to express that these pieces of information are bound together in describing a discrete item, distinct from other items perhaps listed on the page. Semantic HTML refers to the traditional HTML practice of markup following intention, rather than specifying layout details directly. For example, the use of less than m greater than denoting emphasis, rather than less than I greater than, which specifies italics. Layout details are left up to the browser, in combination with cascading style sheets. But this practice falls short of specifying the semantics of objects such as items for sale or prices. Microformats extend HTML syntax to create machine-readable semantic markup about objects including people, organizations, events and products. Similar initiatives include RDFA, Microdata and Schema.org. Semantic Web Solutions. The semantic web takes the solution further. It involves publishing in languages specifically designed for data, resource description framework, web ontology language, and extensible markup language. HTML describes documents and the links between them. RDF, OWL, and XML, by contrast, can describe arbitrary things such as people, meetings, or airplane parts. These technologies are combined in order to provide descriptions that supplement or replace the content of web documents. Thus, content may manifest itself as descriptive data stored in web-accessible databases, or as markup within documents interspersed with XML, or, more often, purely in XML, with layout or rendering cues stored separately. The machine-readable descriptions enable content managers to add meaning to the content, i.e., to describe the structure of the knowledge we have about that content. In this way, a machine can process knowledge itself, instead of text, using processes similar to human deductive reasoning and inference, thereby obtaining more meaningful results and helping computers to perform automated information gathering and research. An example of a tag that would be used in a non-semantic web page. Less than item, greater than blog, less than item, greater than encoding similar information in a semantic web page might look like this. Less than item RDF, about equals, http://example.org/semantic-web/ greater than semantic web less than item greater than. Tim Berners-Lee calls the resulting network of linked data the giant global graph. In contrast to the HTML-based World Wide Web, Berners-Lee posits that if the past was document sharing, the future is data sharing. His answer to the question of how provides 3 points of instruction. 1. A URL should point to the data. 2. Anyone accessing the URL should get data back. 3. Relationships in the data should point to additional URLs with data. Web 3.0. Tim Berners-Lee has described the semantic web as a component of Web 3.0. People keep asking what Web 3.0 is. I think maybe when you've got an overlay of scalable vector graphics, everything rippling and folding and looking misty, on Web 2.0 and access to a semantic web integrated across a huge space of data, you'll have access to an unbelievable data resource. Tim Berners-Lee, 2006. Semantic web is sometimes used as a synonym for Web 3.0, though each term's definition varies. Challenges. Some of the challenges for the semantic web include vastness, vagueness, uncertainty, inconsistency, and deceit. Automated reasoning systems will have to deal with all of these issues in order to deliver on the promise of the semantic web. Vastness. The World Wide Web contains many billions of pages. The SNOMEDCT medical terminology ontology alone contains 370,000 class names, and existing technology has not yet been able to eliminate all semantically duplicated terms. Any automated reasoning system will have to deal with truly huge inputs. Vagueness. These are imprecise concepts like young or tall. This arises from the vagueness of user queries, of concepts represented by content providers, if matching query terms to provider terms, and if trying to combine different knowledge bases with overlapping but subtly different concepts. Fuzzy logic is the most common technique for dealing with vagueness. Uncertainty. These are precise concepts with uncertain values. Probabilistic reasoning techniques are generally employed to address uncertainty. Inconsistency. These are logical contradictions that will inevitably arise during the development of large ontologies, and when ontologies from separate sources are combined. Deductive reasoning fails catastrophically when faced with inconsistency, because anything follows from a contradiction. Defeasible reasoning and paraconsistent reasoning are two techniques that can be employed to deal with inconsistency. Deceit. This is when the producer of the information is intentionally misleading the consumer of the information. Cryptography techniques are currently utilized to alleviate this threat. This list of challenges is illustrative rather than exhaustive, and it focuses on the challenges to the unifying logic and proof layers of the semantic web. The World Wide Web Consortium Incubator Group for Uncertainty Reasoning for the World Wide Web final report lumps these problems together under the single heading of uncertainty. Many of the techniques mentioned here will require extensions to the web ontology language, for example to annotate conditional probabilities. This is an area of active research. Standards. Standardization for semantic web in the context of Web 3.0 is under the care of W3C. Components. The term semantic web is often used more specifically to refer to the formats and technologies that enable it. The collection, structuring and recovery of linked data are enabled by technologies that provide a formal description of concepts, terms, and relationships within a given knowledge domain. These technologies are specified as W3C standards and include Resource Description Framework, a general method for describing information, RDF Schema, Simple Knowledge Organization System, SPARQL, an RDF query language. Notation 3, designed with human readability in mind. NTriples, a format for storing and transmitting data. Turtle, Web Ontology Language, a family of knowledge representation languages. Rule Interchange Format, a framework of web rule language dialects supporting rule interchange on the web. The semantic web stack illustrates the architecture of the semantic web. The functions and relationships of the components can be summarized as follows. XML provides an elemental syntax for content structure within documents, yet associates no semantics with the meaning of the content contained within. XML is not at present a necessary component of semantic web technologies in most cases, as alternative syntaxes exists, such as Turtle. Turtle is a de facto standard, but has not been through a formal standardization process. XML schema is a language for providing and restricting the structure and content of elements contained within XML documents. RDF is a simple language for expressing data models, which refer to objects and their relationships. An RDF-based model can be represented in a variety of syntaxes, e.g., RDF, XML, N3, Turtle, and RDFA. RDF is a fundamental standard of the semantic web. RDF schema extends RDF and is a vocabulary for describing properties and classes of RDF-based resources, with semantics for generalized hierarchies of such properties and classes. OWL adds more vocabulary for describing properties and classes, among others, relations between classes, cardinality, equality, richer typing of properties, characteristics of properties, and enumerated classes. SPARQL is a protocol and query language for semantic web data sources. RIF is the W3C rule interchange format. It's an XML language for expressing web rules that computers can execute. RIF provides multiple versions, called dialects. It includes RIF Basic Logic Dialect and RIF Production Rules Dialect. Current state of standardization: well-established standards. RDF, RDFS, Rule Interchange Format. SPARQL, Unicode, Uniform Resource Identifier, Web Ontology Language. XML, not yet fully realized. Unifying logic and proof layers. Applications. The intent is to enhance the usability and usefulness of the web and its interconnected resources by creating semantic web services, such as servers that expose existing data systems using the RDF and SPARQL standards. Many converters to RDF exist from different applications. Relational databases are an important source. The semantic web server attaches to the existing system without affecting its operation. Documents marked up with semantic information. This could be machine-understandable information about the human-understandable content of the document, or it could be purely metadata representing a set of facts. Note that anything that can be identified with a uniform resource identifier can be described, so the semantic web can reason about animals, people, places, ideas, etc. There are 4 semantic annotation formats that can be used in HTML documents: microformat, RDFA, microdata, and JSONLD. Semantic markup is often generated automatically, rather than manually. Common metadata vocabularies and maps between vocabularies that allow document creators to know how to mark up their documents so that agents can use the information in the supplied metadata. Automated agents to perform tasks for users of the semantic web using this data. Web-based services to supply information specifically to agents. For example, a trust service that an agent could ask if some online store has a history of poor service or spamming. Such services could be useful to public search engines, or could be used for knowledge management within an organization. Business applications include facilitating the integration of information from mixed sources, dissolving ambiguities in corporate terminology, improving information retrieval thereby reducing information overload, identifying relevant information with respect to a given domain, providing decision-making support. In a corporation, there is a closed group of users and the management is able to enforce company guidelines like the adoption of specific ontologies and use of semantic annotation. Compared to the public semantic web, there are lesser requirements on scalability and the information circulating within a company can be more trusted. In general, privacy is less of an issue outside of handling of customer data.